Today we are starting Unit 7, which is Chapter 8 in the book. And as you can see here, we're starting with sections 8.1 and 8.2. So we're talking about Area of Polygons. So before we get started, some of this is going to be information you already know. It's going to be very basic. But what I want you to keep in mind is, as we build off of the basic, make sure that you pay attention to where the formulas come from in terms of how they're derived, because you may be asked to derive them on a test. So here we go. Area, a definition. The area of a plane, figure, or shape is the measure of the region enclosed by the figure or shape. This is a very simple definition, one that you already know. You probably were introduced to it early in life as a child, so this is nothing new. We have two rectangles in the picture here. Basically, you see the one on the right, it has sort of like the grid. If we had such a rectangle, we could simply count the number of squared units and report what the area is. So we could say we have 4, 8, 12, 16, 20, 24 square units is the area of that rectangle. They're not specifying a certain unit, like inches or centimeters, so we would just say 24 squared units, or units squared. Area, as you know, is always measured in squared units. Keep that in mind. Now the rectangle on the left, there are no units being indicated, no squares, nothing we can count, so we have to apply some sort of formula that uses the dimensions. And that takes us to the area of a rectangle formula. This again probably was introduced to you very on in life. The area of a rectangle, the formula is the length times the width. So if you're given those two measurements, you multiply them together, you find the area. If that rectangle happens to be a square, we could think of the area formula as side squared, because of course the length and the width would be congruent. So next we take a look at the area of a parallelogram. Maybe you're familiar with the formula for area of a parallelogram, but it's not as simple as the rectangle, or not as common as the rectangle. Now, the formula for the parallelogram is base times height. Now let me explain where it comes from. We know that a rectangle is length times width. Base times height is similar, but slightly different. If I were to cut off a right triangle from this parallelogram, like that, and move it over to the other side, we see that all of a sudden our parallelogram has become a rectangle, right? So the areas are the same, they're congruent. But the thing is, when we have a rectangle, we have a length, and we have a width. Now you can see that the width is, as a parallelogram, is equal to the height of the parallelogram. Well, the length is no longer the length, that's why we call it the base, right? So if you know the base and you know the height of the parallelogram, you multiply those together and you have the area. Not very complicated. Next we take a look at the area of a triangle. So this is another one that's fairly common from elementary school. Area formula of a triangle is 1/2 base times height, or base times height divided by 2. Now let me show you where this comes from. It actually stems from, or is derived from, the area of a parallelogram. Because if I were to take this triangle and I were to duplicate it, So I have a congruent triangle here. Now if I take it up here and I rotate it around, and I put it into place, I have a parallelogram, right? And I can do this with any triangle. Duplicate it, flip it around, put it right next to the original, and you create a parallelogram. Well, of course, we're not interested in the area of the parallelogram. We're interested in the area of the triangle. So what do we have? We have half of the area of the parallelogram. And that gives us the formula for area of the triangle. Next we talk about the area of a kite. The area of a kite formula is derived from the area of a triangle formula. So you can see how we're building on one after another, right? Okay, so the area of a kite formula is where things start to get a little more complicated. If we draw in a diagonal, right, that connects our vertex angles, then we cut our kite into two congruent triangles. And we know the formula for each of these is going to be 1/2 base times height. Right? Let's call this dotted line, this diagonal, D1, or diagonal 1. So if we're calculating the area of the top triangle, we're going to do 1/2 times the base, which is D1, times the height. Now the height of this triangle is right there. Because we study triangles, though, we know that if we continued that dotted line all the way through, that would be the second diagonal of the kite, right? Okay. But the height of the top triangle is only half of that second diagonal. So if I'm using my formula, 1/2 base times height, I've plugged in D1 for the height. I'm going to plug in half of what we will call D2. Half of D sub 2. So this would be the area of the top triangle. Now the area of the bottom triangle is going to be exactly the same, right? It's going to be 1/2 the base, which is diagonal 1, times the height, which is again half of diagonal 2. So really what we need to do here is we need to double this, multiply by 2. Oh, now we just do a little bit of algebra. 1/2 times 1/2 is 1/4 diagonal 1 times diagonal 2. But then we have to multiply it by 2. 1/4 times 2 is 1/2. So we get 1/2, well, let's just do it like this. We get 1/2 diagonal 1 times diagonal 2. So as long as you know the lengths of those diagonals, you can calculate the area of the kite. Next is the area of a trapezoid. And this one gets even a little more difficult. There are many ways to derive the area of the trapezoid formula. You can cut it a bunch of different ways. You could cut this triangle off and move it over here to make it a rectangle. You could break this into a rectangle and two triangles and add the areas together. Those are slightly more difficult ways because you have to figure out how to name all the pieces that you need to calculate those individual areas. But it can be done. Okay? It absolutely can be done. The method probably that is the best because it can be applied the same way to any trapezoid is cutting the trapezoid into two triangles. They're not congruent, but they are two triangles. Now what we can do is we can apply the area of the triangle formula. Now we know, let's call this base 1, and we'll call this base 2. The area for this triangle is 1/2 base 1 times height. Now the height of this bottom triangle would be the perpendicular that would come right down here. Well, the height of that triangle is also the height of the trapezoid, right? Okay, so we'll just call that 1/2 times base 1 times height. Now, let's look at the top triangle. We know that it would be 1/2 base, well, let's call it base 2, so you kind of got to think of this triangle upside down, times height. The height of this top triangle, we have to extend this. The height of this top triangle is the altitude that falls outside of the triangle. But that height is also the height of the trapezoid. So we can just call it h again. We have different bases, but we have the same height for each triangle and the trapezoid, right? So now we can take those two area formulas and add them together. Make some space here. So 1/2 base 1 times height plus 1/2 base 2 times height. And you should be writing this down in case it's a test question. And now we can factor out the 1/2 and the height because they're like terms, they're common factors. So we factor out 1/2 and the height, and what are we left with? Base 1 plus base 2. And we know this as half the height times the sum of the bases.